The production of tangible goods beyond Earth, known as space manufacturing or in-orbit manufacturing, has become an area of increasing interest. The space environment, with its unique conditions, allows for research and production that would otherwise be impossible on Earth. The extraction and processing of raw materials from other astronomical bodies, also known as in situ resource utilization, could reduce the cost of space exploration missions and could lead to greater sustainability. High-value materials, such as gold, silver, and platinum, could be transported to low Earth orbit for processing and transfer to Earth, making this an economically feasible option. Since the 1960s, space manufacturing experiments have been conducted, with the Skylab mission being equipped with a materials processing facility for various experiments. The Space Studies Institute has held a biannual space manufacturing conference since 1977, and microgravity research in materials processing has continued through various space missions and facilities. The potential benefits of space manufacturing are vast, and continued research in this area could lead to exciting developments for the preservation and advancement of our planet. The theme of this story is the unique properties of materials in space, and the potential for exploiting these properties to improve manufacturing techniques. The microgravity environment offers advantages such as controlled convection and enhanced crystal growth, while surface tension can cause problems when pumping liquids but is useful for creating round spheres of consistent size. Space also provides extremes of heat and cold that can be exploited to produce strong, glassy materials. Raw materials can be obtained from asteroids, the lunar surface, or other planetary bodies, and propulsion techniques such as solar sails or electric ion thrusters can be used to move them to processing facilities. Once captured, the materials can be moved into place by mechanical means or by small thrusters. The core theme of space manufacturing is the need for readily available sources of useful volatiles. Processes such as extracting oxygen from the lunar regolith or purifying asteroid materials with the use of carbon monoxide, CO, have been tested. One major factor that needs to be considered is the distance from Earth and the communication constraints. Thus, space manufacturing would require either completely autonomous robotics or human crew members with all the requisite safety and habitat requirements. Solar power provides a readily available power source and is integral to thermal processing. Glassy materials can be used for the assembly of habitats on the Moon or elsewhere. Similarly, the availability and favorable physical properties of metals, with significant modifications due to the microgravity environment, will make them a major component of space manufacturing. The production of hardened steel in space, however, will introduce some new factors, such as the need for carbon and water from other sources. The theme of the story is the development of manufacturing techniques in space, specifically the potential of 3D printing. Several methods of metalworking are available in space, including casting, drawing, forging, machining, rolling, and welding. However, 3D printing holds numerous advantages, including easy customization, minimal raw material waste, and faster production time. The concept of 3D printing food items is also being investigated. Made in Space Incorporated has developed a 3D printer specifically for the microgravity environment of space. Meanwhile, the refabricator experiment is being used to evaluate the feasibility of closed-cycle in-space manufacturing. Airbus is partnering with the European Space Agency to develop the first 3D printer for printing metals in space, with the potential for space manufacturing to be established within 3 to 4 years from 2022. The theme of the passage is the potential for space manufacturing and its various applications. With the development of infrastructure and decreased assembly costs, larger-scale manufacturing plants can be constructed in space using lunar and asteroid materials. Rock can be used for radiation shielding and processed to extract necessary elements. Water from various extraterrestrial sources is cheap and easy to extract, making it useful for manufacturing and material shipping. Ceramics and metals made from lunar or asteroid soil can be used for various purposes, including insulation and solar panels. The microgravity environment allows for new, innovative constructions such as space elevators and rotating habitats capable of sustaining Earth-like conditions. Ultimately, these space manufacturing facilities could become self-sustaining and require minimal imports from Earth. The central theme of this story is the economic feasibility of space manufacturing. In order to meet this objective, it is imperative to gather raw materials at the lowest possible energy cost. One crucial factor in this equation is the cost of space transport, which is inherently linked to the delta V, the alteration of velocity required to move between mining sites and manufacturing facilities. While launching from Earth is an expensive option, sourcing materials from near-Earth asteroids, Phobos, Deimos, or the lunar surface is economically advantageous due to the minimal delta V required as a result. These locations are highly attractive as sources of raw materials for space manufacturing.